So far, all the functions that we've written have had a fixed number of arguments. But MATLAB has built-in functions that are much more flexible. For example, have you ever wondered how fprintf works? Specifically, how can it take any number of input arguments? For instance, in this example behind me, we're giving it 4 arguments, the format string and 3 numbers. But we could put all the %Ds and %Fs and all the other format operators that we want in this format string and then simply add the same number of additional input arguments to match up with them, and it'll work just fine. There's really no limit to how many input arguments we can pass to fprintf. That's one of the special things about it. Of course, fprintf is built into MATLAB, so it's not all that surprising that it has special privileges, like taking an unlimited number of arguments. But what might be surprising, though, is that you too can write a MATLAB function with an unlimited number of arguments. How do you do that? Well, we're going to find out right now. Before we show a function that handles an unlimited number of arguments, let's look at a function that does not. It's called findFirst, and we're showing it because it calls a special function that we will use when we do get to an unlimited number of arguments. Remember our old friend nargen? Some people call it nargen. We talked about it in the 5th lesson of our introductory course. Well, if you don't, no worries. It's very simple. It's a built-in function that returns the number of actual input arguments supplied by the caller. There's one just like it named nargout for the number of output arguments requested by the caller. By the way, in the language of computer science, the values supplied by the caller for the input arguments and the variables supplied by the caller to hold the output arguments are called the actual arguments. This function takes 2 input arguments, v, which is assumed to be a vector, and e, which is assumed to be a scalar. We could add code to verify these assumptions, but we're not going to bother with it. The function is called findFirst because it finds the first element of v that is equal to e. If the second argument e is omitted by the caller, the function finds the first element of v that's equal to 0. And if it doesn't find what it's looking for, it returns 0, which is a forbidden index in MATLAB. The if-else-if statement here uses nargen to determine whether the function was called with no input arguments, in which case it throws an error, or was called with just 1 input argument, meaning that the caller supplied a value for v but not for e. If it was called with just 1 input argument, then instead of throwing an error, the function assigns the value 0 to e, which means that when it does its search for e, it will be searching for 0, as required by our specifications. The rest of the function is not our concern now, but you can study it on your own to understand how it works. Let's run it on a few different inputs. First, we'll get a vector of integers from the built-in function randy. We'll get random integers from -3 to +3, and we'll get 12 of them in a row vector. And just before that call, we call RNG to initialize the random number stream so you can duplicate what you see me do. And now let's use our function to find some integers inside W. As you can see, it works just as we expected it to. It found 1 at index 5 and 0 at index 8. And when we look for something that isn't there, like 12, it returns 0. Finally, and most importantly, when we didn't supply a value for the second input argument, as in the last case here, it searched for 0 and found it again at index 8. So, nargen is very nifty, but can we use it to implement a function like fprintf? Well, let's talk about that. First, let me clear the command window. And now I'm going to type into the editor window a lame attempt at a header for our own fprintf function. The function header is also known in computer science as the signature of the function. It determines the name of the function, the maximum number of output arguments, which in this case is 0, and the maximum number of input arguments, which in this case is 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, and while we're trotting out all these computer science terms, we might as well mention that the arguments whose names are given in the signature are called the formal arguments, as opposed to the actual arguments that the caller uses when the function is called. In the body of the function down here, we can then use nrgen to determine how many of the arguments were actually supplied with values by the caller. This works to an extent, but what happens if fprintf is called with 10 arguments, or 11, or more? Well, I can tell you what happens, and it isn't pretty. There's an error, there's a message, it's read, it's bad. Of course, we could add some ridiculous number of input arguments to the signature above, but it'll always be a fixed number. And if we need to call it with a ridiculous number of arguments plus 1, well, you can see this just isn't working. Not to mention the pain of typing zillions of argument names into the signature. I'm already tired from typing just these 9. Okay, there has to be a better way. And I'm sure you've figured out that there is. The better way is called varargin. And we've written a simple little example function that uses it. It's called printall. Varargin shows up here as a formal argument in the signature. Its name stands for Variable Length Input Argument List. It's a special input argument that is actually a cell vector, and MATLAB packs multiple actual input arguments into it, and there's no limit placed on the number of actual arguments that it can hold. That's perfect for our little printall function because its job is to print an unlimited number of actual input arguments. The only restriction that printall places on those actual arguments is that they all be scalars. Once again, we could add code to confirm that restriction, but we're not going to bother with it. Let's run it on some inputs. Let's give it just a single argument, pi. And there it is, and it prints this little message. Here is input argument number 1, and there's the value of it, and you can see it's pi. Let's try 2 arguments, 7 and minus 3. And this time, since it got 2 input arguments, it prints 2 lines, one for 7 and one for minus 3. And let's print a bunch of them. And you can see it works for a bunch of them too, and it will go on and on and on and on, no matter how many we put in there. It works, and it does it by simply running this for loop through all the elements of varargin and printing each of them on a separate line. There are 2 things to note here. First, nargen still works. It provides the number of actual input arguments. Even though we declared a single formal input argument, varargin, nargen will return the number of arguments supplied by the caller of the function. Second, since varargin is a cell vector, we have to use curly braces here in order to pull out the actual arguments that are stored in it, so we can pass them into fprintf. Regular parentheses would provide a cell argument, and fprintf can't print those. One more thing to note, and this is a pretty big one. Varargin does not have to be the only input argument. The signature can include any number of arguments, but if it includes varargin, it can have only one varargin, and varargin has to be the last one. Basically, varargin is a catch-all that stores all remaining actual input arguments beyond the ones explicitly listed as formal arguments. Now that we know what varargin is and how to use it, let's look at a more complicated example. Let's write our own version of sprintf, which is the sister of fprintf. Sprintf, which is sometimes pronounced sprintf, is very much like its brother fprintf, It takes an unlimited number of input arguments, and its first input argument is a format string that is used in exactly the same way as fprintf uses it to format the output from all the rest of its input arguments. The only difference between sprintf and fprintf is that instead of actually printing the result, sprintf puts its results into a string, which it then returns as an output argument. Here's an example. As you can see here, we put in the phrase, the first three positive integers are %d, %d, and %d as a string. In fact, it's the format string. And then we gave it three remaining arguments, 1, 2, and 3. And it formatted 1, 2, and 3 using the %d integer format. And this result is a string, as we can see by the quotes around it, here and here. Our version is a little bit simpler than the built-in sprintf. It processes only numerical inputs. It does not allow field width or precision before the %sign, and it supports only the conversion characters D, F, and E after the %sign. Here's our function, which is named printNum and takes up a bit more space. Let's give it a little room here. There. The first formal input argument is the format string, and the first actual input argument will be assigned to it. All the remaining actual inputs will be stored here in var_argin. The output will be stored in the variable out, which we initialize to the empty array right here in the first command. The variable arg_index here is used to store the index of the element of var_argin that we are currently dealing with. The logical variable skip is used when we encounter a %sign. When we do, we know that the next character is the conversion character, and we process it right then. So in the next iteration of the loop, we need to skip it. The for loop examines each character of the format string one by one. If skip is true, then we need to skip a character. To do that, we simply do nothing on the current iteration and go to the next one, setting skip back to false before we do. Otherwise, if the current character is not a %sign, we simply add it to the end of the output string. Otherwise, we check whether this % is the very last character of the format string. If it is, then we're done. So we execute the break statement, which ends the loop, and we return. Otherwise, we determine whether the next character is another %sign. If so, we add it to the output string, because 2 %signs in a row means that 1 %sign should be printed. Otherwise, we determine whether there is at least one more actual argument in var_argin. If not, we throw an error, because there must be one argument in var_argin to correspond to each format operator in the format string. If so, we use the built-in number-to-string conversion function num2str here to convert that argument to a string, using as its second argument the format operator consisting of the %sign followed by the next character in the format string. Then we increment arg_index and iterate again. And that's it. Okay, let's see our function in action. We'll start by giving it exactly the same set of arguments that we gave in this example with sprintf. I'm going to hit the up arrow key, and I'm going to slide over here to the left, and I'm going to change function name from sprintf to printNum. And it works. Let's do a more complicated example. Well, I'm not going to make you wait for all this. I'll just compress time for you. You can see in this example that we put 2 %signs in a row here, and as we mentioned, that means that 1% is to be printed, and neither one of the % signs is to be treated as an operator. And here we see that 1% sign coming out here, as expected. So it's working well. But what happens if the number of operators in the format string doesn't match the number of arguments contained in var argin? Well, let's try an example with one operator in the format string and two operators in var argin. Well, that's not so bad. Our smart little function had the good sense just to ignore the second argument in var argin, which is exactly what sprintf does, by the way. Now let's go the other way. We'll put two operators in the format string and only one argument in var argin. Well, it looks at first like we've made MATLAB mad and it slapped our hand. But if we look again at our function up here, you'll remember that this case is caught in the code and it threw an error with this very error message. We slapped our own hand. So to summarize, our function works as expected for correct inputs, and if the caller supplies too many input arguments, nothing bad happens. The function uses only the arguments needed by the format string and ignores the rest. However, if the caller doesn't supply enough input arguments, our function's error handling facility provides an informative error message. So that's how you write a function with an unlimited number of inputs. You do it with var argin, and as you can see, it's really easy to use. So what about going the other direction? Can you write a function with an unlimited number of outputs? Yes, you can, and in rare cases, you just might need to do it. Suppose, for example, that we want a function that'll take an input vector and copy the value of each of its elements into a separate output argument. We can accomplish that with a sister of var argin named var argout, and we've written a function called distribute that does it. Var argout here is very similar to its sister. Both sisters act like arguments, and both of them hold variable numbers of arguments in a cell vector. I'm guessing that you can see at a glance how distribute uses var argout to accomplish its mission. The elements of V are assigned one by one in the for loop into cells of var argout, and var argout serves as the only output argument. As an example of a call of this function, let's give it an actual input argument that has three elements, and also give it three actual output arguments to receive those three elements. The three elements of the actual input argument are distributed to the three actual output arguments as expected. Great, it's working. And you now know how to use var argout to handle a variable number of output arguments. We could stop right here, but I wonder what would happen if we left out one of the actual output arguments. Well, if there aren't enough output arguments to hold all the elements in var argout, they are simply ignored. No error, no problem. But things aren't so nice if you go the other way. That is, if there are more output arguments than elements in var argout. Let's try that right now. And brace yourself for trouble. A big, ugly red error. And this error message came from MATLAB. It would be better if the function itself checked the length of var argout against nargout and called the error with a better message. Like, say, the number of output arguments cannot be greater than the number of elements in the input argument. You should try modifying this function yourself to give this error, or whatever error you'd like. One last detail that we should mention is that, just as with var argin, you can include normal local variables along with var argout in the list of formal output arguments in the function signature. But, as with var_argin, var_argout must be the last argument in the list. In analogy to var_argin, var_argout holds any excess output arguments that come after the normal ones. Alright, we've relearned what nrgin and nrgout do, and we've learned what var_argin and var_argout do. The first two count arguments, and the second two store variable numbers of arguments. And that's how MATLAB allows you to define functions that can handle unlimited numbers of arguments.